Hey guys, welcome back. We are now looking at doing triple integrals in cylindrical coordinates. And so the first example we're going to do here is to use cylindrical coordinates to set up the triple integral of region E of x squared plus xy squared dv, where E is the solid in the first octet that lies beneath the paraboloid z equals 1 minus x squared minus y squared. So one of the things that I really like doing first is to visualize what we're trying to take the volume of. So the first thing we're going to do is we're actually going to sketch this paraboloid. And one of the things that I think is very easy for us to do is actually look at what's happening in each of our three planes. So what do I mean by that? So if I look at the plane of xy, that means that z is actually going to be equal to 0. So if we make z equal to 0, and then I move the x squared and the y squared over, I get the equation of x squared plus y squared is equal to 1. So this is a circle that's just in this xy plane that has a radius of 1. So I'm going to go ahead and draw myself a little circle of radius 1. And so that's going to be what's going on right there. Then similarly, I'm going to go ahead and do the same thing, and let's see what's going on in the YZ plane. So what's going on right here? Well, I'm going to make that where x is equal to 0. So when x is equal to 0, I get the equation that z is equal to 1 minus y squared. Well, that's awesome. This is a parabola that has a z-intercept at 1, and it actually is going to go to y equals 1. And so that's my second region. And then very similarly, if I make y equal to 0, then I can say that z is equal to 1 minus x squared. So same thing before. We're going to look in the zx coordinate plane, and we're going to go ahead and have our parabola look like this. And so the region itself, the parabola itself, is actually going to have a little bit of structure to it, three-dimensional structure. And so this is going to be what we're actually trying to take the volume of. So the first thing that we're going to do here is we're going to look at the fact that when we're looking at polars, right, cylindrical coordinates, we're going to do r, theta, and then z, right? So these are going to be the three integrals that we're going to actually set up in this particular problem. So the first thing we'll do is let's just start talking about the theta. So what is my range for theta? Well, we're going to first of all say that we're starting at the positive x-axis, which we know that theta is going to be equal to 0. And since we're in just the first octet, right? So we're only in the first octet here. We're going to travel along until we hit the y-axis, the positive y-axis, and that's going to give us pi over 2. So theta is actually going to be from 0 to pi over 2. The radius, well, the first part is the radius is actually going to start right here along our xyz, right here at our pole. And so the radius, the small radius, is going to be 0. And so what I want to do here, because we're going to need to convert this into our polars, cylindrical coordinates, is we're going to do z is equal to 1 minus. Remember that x squared plus y squared is equal to r squared. So x squared plus y squared is equal to r squared. So if I take the negative out, I'll have x squared plus y squared, so I can replace x squared minus y squared, right? If I pull a negative out of this, then I'm left with x squared plus y squared, which is r squared. So I actually can set 0 equal to z equal to 0 in this case. And when I set z equal to 0, I get that the radius is going to be equal to positive or negative 1. But in this case, because radius is always positive, our radius is going to be 1. And that's going to be what's on this curve, right? On this peak curve that I've drawn right here. And then z is going to be between, well, we can say that the bottom part of a paraboloid, z, is going to be 0, right? Because that's going to be our bottom. And then anywhere on the curve is actually going to be the function of 1 minus r squared. So those are going to be the bounds that we're going to start setting up, right? So we already actually have our bounds. So we're going to always go with theta first of 0 to pi over 2. Then we're going to go ahead and do the radius, which is 0 to 1. And then our z component, which are going to be our surfaces, are going to be 0 and then 1 minus r squared. All right, so now what we're going to do is we have to convert everything. So we're going to use a couple of equations that we should be familiar with. So remember that x is always equal to r cosine of theta. and that y is also equal to r sine of theta. So everywhere I see an x, I'm going to write the r. So I've got r cosine of theta quantity cubed. So it's going to be r cubed cosine cubed theta. And then I got another x right here. So I'll go ahead and write another r cosine of theta. And then we have a y squared, which is going to be a r squared sine squared theta. And all of this is going to be the expression for x squared, or excuse me, x cubed plus xy squared. And then we're going to, and let's not forget this, guys, we always have to put our r, right? And then we're going to do dz dr d theta. So that's really the setup of this problem. However, I want to simplify this a little bit better because it wants us to set it up, and I want to just make it a little bit easier for us. So one of the things I want us to understand here is we have an r cubed in the first term, and we also have an r cubed in the second term, right? So an r times r squared is r cubed. We both also have a cosine of theta in both of them. So we're going to pull that out, right? So what's left here in this first term, if we pull out the r cubed and one of our cosines, we're left with cosine squared theta. And then when we have the r cubed and then the cosine, we're left with sine squared theta. So our favorite identity that we all know and love is actually going to be that cosine squared plus sine squared theta is equal to 1. And we still have this one extra r here, right? So when I finally put our final answer to what I want to finish this problem with, so our theta is between 0 and pi over 2. Our radius is going to be from 0 to 1. Our z value, z function, is going to be from 0 to 1 minus r squared. And I've got r to the 4th times cosine of theta. And then we're going to go ahead and plop down our dz, dr, d theta. So this is the integrand that we want to use that's very simplified. So if we were to actually start integrating this, this is where we want to start with the problem. So we start out with a really easy, pretty straightforward example. Even though it looked really complicated right here, we actually worked it out for us. So that's all we have for this particular example, and I'll see you guys when we do the next example. Take care.